So my work this summer involved using the FTIR ATR to collect time resolved data measuring the diffusion coefficients of the salt LiTFSI and the black copolymer SEO using varying temperature gradients and salt concentrations. So the main goal is seeing how these impacts this rate coefficient, as well as using proving that this is a repeatable and effective technique. So a little background on the FTIR. This is the machine I used in lab this summer. It is a way to provide a non-destructive and air-free environment. The ATR crystal and anvil are both separately feedback controlled, so it detects any asymmetry. I used an MCT detector, which is a high sensitivity and low signal to noise ratio. This was needed for the small magnitude of the diffusion coefficients, and it can also make a temperature gradient easily induced or removed. It can go up to 80 degrees Celsius per minute. The Surrey effect is defined as the ratio of thermal diffusion to thickening diffusion. It's measured at steady state and has great application for rechargeable lithium metal batteries, membrane separation, and thermal galvanic cells like the one shown to the right. This greatly improves energy efficiency as they're powered by a temperature gradient as opposed to a chemical potential gradient. So for my sample preparations, I made 2 samples of molar ratios 0.1 and 0.05 moles of lithium to ethylene oxide. I then used a custom anvil design as shown to the schematic I made on the right. The water bath cools the copper anvil, and then the ATR crystal and base plate is heated using the Golden Gate. This creates the desired temperature combination. As the 3 combinations shown beside me, I had to use multivariable linear regression formula to code the variables, so due to temperature bleed. I then used liquid nitrogen to cool excited electrons and induced a temperature gradient, which ran for 6 hours, and I removed it and got the thickening diffusion coefficients. This graph is the CF3 peak of LiTFSI, which when integrated and normalized gives me this graph, which shows the numerical model and an analytical model. The numerical model gives us the coefficients that are shown in the table. I use an Arrhenius relationship because the diffusion coefficient and temperature, by taking the natural log of both sides, it makes it easier to graph and analyze. So all analyzation was done in this format. All this data is in good agreement with previous data, which proves the effectiveness and repeatability of this technique. So why should you care? A lot of energy is wasted every single year. So there's clearly a need for work to be done in the battery field on making more efficient batteries. And this will also prove as a good basis for future work on the Surrey effect, which I plan to do with varying the salt molar masses, lithium perchlorate, lithium triflate, and also bringing my data to conferences in the fall. And yeah, thank you to the whole Polymers of Advanced Energy and Sustainability Lab and Dr. Hellman too for helping me this summer. Thank you.